For the introduction and for your invitation to the workshop. My name is Ioannis Ivrissimtzis. I'm from Durham University, and I will present some work on how we measure bias, especially on classification problems, and what we will use is sample size analysis. So this is joint work with Matthew Hulliston and Graham Roberts from Serve Legal, which is a company here in London that they do compliance and auditing services, and Sona Concano, who is my colleague, she's my colleague in Durham University. So what I will talk about is, I think I jumped one. Yeah. So first I will state the problem and how we approached it. Then I will give an example, the chi-square test on a data set comprising two demographics, and then I will do some comparison with different approaches, which is basically the differences and ratios of error rates. So what is the problem? First of all, there are several measures to assess the performance of a classification algorithm. I just mentioned randomly here a few of them. The question we want to address is how we measure bias, which here we understand it as the differences in the performance of the algorithm between various demographics of the dataset. So demographics here, think of subsets of the dataset. The common practice is to compute and report performance metrics, so these metrics here, to compute them and report them on each demographic separately. And also sometimes some basic comparisons between these results. So we say the TFR here is 2% higher, the FNR is, let's say, 20% higher, and so on. So let me now first state the problem a little bit more formally. We have a data set. It consists of various demographics, so think of them as subsets. In the simplest case that we'll deal here, we have two demographics, two subsets, and we deal with the performance measure, which is the error rate, so let's say the opposite of accuracy. And we know that in the demographic, one is E1, and the other is E2. So what I would like to stress here is that in our settings, the error rates are given. So we know that this algorithm performs so well or so bad in this demographic, so well or so bad in the other demographic. Now, what we want to measure is the significance of any differences between E1 and E2. So it's a kind of a black box approach. Remember that our motivation basically is auditing and compliance. So we don't aim, let's say, to understand bias, how it occurs. We don't want to we don't aim to fix it. We just want, at this stage, to measure it. So our proposed approach is, the main idea is to compute the sample size of a statistical set that would detect this bias. Okay, so if the bias is small, if the error rates epsilon1 and E1 and E2 are close to each other, if I do a statistical test to compute its sample size, it should be large. Okay, it's difficult to tell them apart. If the bias is large, if the performance is very different, I could be able to detect it statistically easily, okay, with a small test. So while the main idea sounds a little bit inverted, have in mind that it is quite common to say, okay, how different are two things? How different is E1 and E2? We say, okay, how much effort do I need to tell them apart? So our basic principle is that the bias is inversely commensurable to the sample size of n. I will not give a direct definition. You can think sometimes, because then we'll fall into some complexities we want to avoid with, let's say, what if n, I compute it as 0 and so on. So you can think as 1 by n or minus log n. But obviously there are some complexities now. Which statistical test should I use, and what parameters should I apply on this test? So here is, to illustrate, let's say, the basic idea. We'll do the chi-square test on two demographics. So we have a classifier on a data set, two subsets, D1 and D2, two demographics. We'll do sample analysis on the chi-square test to detect bias. So the two, let's say, if you think of the contingency table, in one thing we have, in one dimension, we have D1 and D2. On the other, we have correct classification or wrong classification. You can think as a binary classification if you want, but then you might get a little bit confused between the classification and the two demographics, or you can think of basically any type of classification. It just has a binary outcome, correct classification or incorrect. And in that case, we have a good approximate formula, so that means under some reasonable assumptions for approximating some continuous distribution with discrete ones, we have this formula which says that the sample size should be half Z beta, Z alpha, then arcsine. Here are where the error rates on the two demographics appear, and all this square. So this E1 and E2 are the error rates, the level of significance of the test. So in a statistical test, we have to define level of significance and the power. So it's alpha, and then the power of the test is beta. And Z, here is just the critical value of the normal distribution. So if I give you beta and alpha, you just go to a table with the normal distribution and find Z beta and Z A. So here it's how it looks like, the color map of our biases when I have the error here reducing and the error on the other demographic reducing. I color map it. I put logarithm in the color map because otherwise we'll have millions here. And the first thing we notice is that here it's the high values are here. Okay, so this is good. Remember, high values means a large data set, a large a large sample size, which basically means it's difficult to tell them apart. Okay, so obviously when the errors are similar, it should be difficult to tell them apart. I need a large test to run. So it's like this. What we can say is that here basically in that diagonal it goes to infinity, the sample size, so the bias go to 0. Okay, if the errors are equal, the bias is 0. We can find it analytically. We can show this analytically easily, but we can also argue that if I have a statistical test and I want to say two things are apart, they are very, very similar, I need a very large test set. Okay, so one other thing is, what about the alpha and the beta? Generally, metrics are not scale invariant. Okay, so Euclidean distance is not scale invariant, for example. So, if you mix miles with kilometers, we'll have a problem. So the same here, but the sample size depends on these arbitrary parameters of alpha and beta, but only up to a multiplicative constant. Okay, so remember, these are numbers basically defined as functions of beta, a function of A, and these are, at the end, it's a constant. So if I want to quantify bias as a function of its error rates, I can do this with this formula up to a multiplicative constant. What I can do without worrying about multiplicative constants is to rank the two classifiers. Okay, so if one is more biased classifier than the other, so if this one of one classifier is larger than the sample size required for the other classifier, then it will always be the case irrespective of A and B. So for that case, for that reason, we'll concentrate here on ranking, so we don't worry about this multiplicative constant. So what I want to do now is to compare it with error differences, the proposed, let's say, Bayer metrics. So E2 minus E1, the difference of the error rates, and then I will do the same with ratios. So the first thing is that we want to show that it is essentially different. Okay, so I didn't just apply a function and then I just put some numbers, but nothing really changed. And you can see in this example, here I have three classifiers. Here are the error rates in the first and the second demographic. And you can see that, for example, 30% error, 40% error. This is large, so this is very biased. Okay, so this is less biased, this is less biased according to this. Now, if you do the proposed approach, you see it differently. So this one is less biased than this one. Why this happens? I mean, how we can explain it. So what we can notice is from that sample size formula can be shown that when the error rates are kept constant, so when, for example, it's always 0.10%, the difference between the error rates, as I become more accurate, okay, I also become more biased. Okay, so here, you can see here, smaller data sets, smaller sample sizes, I can tell them easily apart. You can see the case. So what we think, let's say, we claim is that this is consistent, aligned with our human perception of what bias is. Okay, so here is, let's say, correct classification and misclassifications in two demographics, and one is 50%, the other is 49%, and you cannot tell them apart. If this was, again, 0.01%, but this time 1% and 0%, you can immediately tell them apart. So this formula tells you biases, how large they are, according a little bit or up to a point to human perception. Now, the second thing is to compare them with the error ratios. So sometimes we don't say this algorithm is 2%, this error rate in this demographic is 2% higher. We say it's maybe, higher by 2%, but it is 20% compared to the baseline, for example. So we'll compare with E2 by E1. And again, first I have to show that this is different. Okay, what we propose is essentially different. You can see here, this is 2 times more likely to have error. This is 3 times. This algorithm is 5 times more likely to have an error. So they are 1, 2, 3 by error. Oh, this is by error ratios here. That's a mistake. Again, if you run our example, you find the opposite ranking. Okay, so somehow a 25% between 25% difference here is less, it's more biased than, 2 times, so this is 0.5 is 2 times this, but this still is more biased compared to this case. Again, we can do again the same and see now that from the sample size formula, that when the error rates now, the error ratios, again differences, it should be ratios here. When the error ratios are constant, as I get more accurate, I get less biased. Okay, so here is 20%, 40%, 10%, 20%, 5%, 10%. So the error ratios are the same. However, the sample size increases, so it's more difficult to tell these two apart than these two. So this is less biased. So why this happens? I think that the most illuminating thing to do is just to draw the contour lines of here the differences, here the ratios, and the sample size, and you see exactly, basically, what happens. And the problem with the ratios, which I think they shouldn't be used when we go towards more accurate algorithm, is that as we go here to 0, 0, so I always go to the accurate algorithm that doesn't make any error at all, there is a singularity. Okay, it depends on how the way I approach it. Okay, if I approach 0, 0 this way, I have high bias. If I approach it, let's say, this way, I have low bias. Now, have in mind, this is not, let's say, any point in this diagram. Okay, you can say, okay, you have infinite many points that you are good, you know why you concentrate here. Okay. So here is basically the point that our work is to take an algorithm and reduce its error. Okay, so our work is taking a point here and moving it towards there. So it depends if you count bias this way. As you get more and more accurate, you will get erratic results. This is not the case here, but it's different. You know, it has different problems. I think it's not so well aligned with our perception, and it's not a problem with the proposed one like here. Now, why, the next one will be my last slide, why this is not a problem, you know, why if I go from any direction, I'll go here to 0 bias smoothly, because obviously an accurate algorithm doesn't have any bias. So here, I want to go to infinity sample size, so to 0 bias. Again, I can use the formula, but I will just use the same trick, the heuristic. Okay, just to show you the generality of the approach. So imagine, for example, that we have 3 demographics. The error rates are E1, E2, E3, and I define my bias as something inversely commensurable with the sample size analysis, where the statistical test hypothesis is that the errors are equal. Okay, there is no bias. And the proof is very simple. Okay, the sketch at least, that any proper statistical set should require some negative samples, okay, some misclassifications. If these are very low, so if we are very close here, so if we are very close here, I cannot get, I need to run my algorithm many times to get even a single misclassification, let alone enough misclassification. So I need a very large data set, so I have very small bias according at least to the proposed measure. And I finish here.